yesterday, this is where we finished. And again, you guys have seen all this. We talked about, and I don't remember exactly where I wrote it down. It may still be in here, right here. Yep. So again, net ionics for acids and bases. If it's strong, you're going to write the ions. If it's an acid, you'll write the hydrogen or the hydronium. If it's a base, you'll write the hydroxide. Again, strong always wins, and we'll kind of get into that a little bit later on. And then weak, you'll write the entire compound. So again, if it's strong, it's H plus OH minus yields the water. If it's a strong acid and a weak base, it's the hydrogen ion plus the base yields some form of a hydrogenated base compound. And we saw this two examples. Yesterday we saw ammonia turn into ammonium when you mix it with an acid. Then we saw methylamine turn into a hydrogenated compound of itself. Go ahead. Base is the B stands right here where it says B, that stands for the base, and whatever the base is. Okay. Now, this is a strong base weak acid. So again, if it's a weak acid, it's HB, and B is whatever the anion is. It could be HA specifically because it's one of the things that you guys saw on that strong acid base PhET simulator that you did. And so then the hydroxide is going to be your strong base anion, and notice what you get. You get water, and you get the anion of the acid. Okay, does that make sense? Okay, it could be any anion. It could be nitrous acid. So that could be NO3. So I think here's a matter of fact, wow, that was a good guess. So you've got nitrous acid, potassium hydroxide plus yields water plus KNO3. So if we were to look at it from a perspective you guys have seen before, would you agree that this is an acid? Would you agree that this is a base? Acid-base reactions produce water and a salt. Okay. Now, the reason that we look at it from a net ionic perspective is that this acid, we write the whole thing because what percentage of it dissociates? Less than 5%. So we're going to keep it as the entire thing. Okay. But this is a strong base. What do we know about strong? It dissociates 100% into K plus OH minus. Does that make sense? Now, stay with me, and this makes sense if you look at the BBC perspective. I'm going to come back to you, Chance. This salt, would it be soluble or insoluble, and how do you know? Very good. So we've got group 1, and that right there. So when we went through our canceling method, how do we know if it canceled or not? If it looked the same. Okay, does K plus look the same? So if you get rid of it, does that make sense why you do not see it in your net ionic? Does the hydroxide look the same? No, who is it now hooked up with? Water. Do you agree that when we're doing acids and bases, you can write water like that because it makes more sense of how it stands? Okay, and what state of matter is this water in? It's liquid. Remember, we always write solids, liquids, and gases as whole entire things. Okay, and then the last thing, does the nitrite, does it look the same? No, it went from the compound to the ion. Does that make sense? So that's why you have to keep it. Chance, you were first. Okay, and that's a good observation. The reason why there's no weak acid, weak base is because it's the whole thing for both of them, so there's not really a net ionic version. It's a normal, regular reaction that you've always written. There will be no ions present. Okay? Not Chance, but Justin. You tell me. You just answered that question. You just told me it's insoluble. It is, so it's not a precipitate. Soluble means it will not precipitate. Does that make sense? Because solubility references is it a precipitate or not. If it's soluble, it is not a precipitate. Yes. Exactly. Yep. Any other questions? Go ahead. Yes. Because it's soluble. Okay? Alright, so here's what I want you... Did this go over in the video? Good, I'm not doing it. We did all that, we did all that, we did all this. Yep. Alright, this is where we stop. Remember, one of the biggest things that I'm pretty sure I talked about in the video, but I want to talk about it in person, is when you're reading meniscus levels. Okay? I want you to, and again, I may have said this, but I want to say it to you in front of your face. Always estimate one value. Okay? Always estimate at least one value. So, when we're looking at that really zoomed in picture of the graduated cylinder, the reason I say at least one value, okay, you want to go to the point where you are not exactly sure because there's no other graduation part to read. So, would this water level be between 40 and 39, right? Is it 40? No. What is it? It is 39. It's tricky, but why is your 1 in 10th place not 40? Has it gotten to 40 yet? No, it's still prior to 40. So it's 39. Okay, that's a good question. Why is it backwards? When we get into titrations, and I've showed you this, remember, so when I turn this little knob and let the water out or whatever it is, do you agree that it's going to be going down the tube? Exactly. So my question to you is if it were 50 at the top and 0 at the bottom, and it got to here, it would go from 50 to, let's pretend that this was 30. Well, how much went out? However, if it were the opposite, if it were 0 to 50 and we stopped here and that was 20, how much easier is that? It's a lot easier to do it when it's going out the bottom versus coming from the top. I know it's a backwards way of thinking about it, and I showed you guys a burette, right? I showed you? Go in there, go around the fridge, and to the right of the fridge, there's a bucket full of burettes. Just grab one. Burettes. Right here. B-U-R-E-T. Burette. Doesn't matter what... Huh? A burette, yeah. Yes. Okay? So, read the number at the top. Okay? We'll read the number at the bottom. 50. So pass that around. So when you see that, that'll make a little bit more sense. So when you turn that little blue knob at the bottom and the liquid comes out, it's easier to read it from that perspective. Nicole, you with me? Y'all going to have to fix that issue. Okay? Yes. Put some in there and pour it out. I mean, I really don't care. You may... Yeah, I don't have anything to pour it in there with. See if you can kind of tilt it and pour it in there sideways, just to fill it up enough. What? Now, so let me go through this again. You've seen this, Dustin. What are you doing? No. Come on. You gotta wait. Can I teach? Please? Okay. So when we look right here, what does each line represent? How much of a value? Each line represents at least 1/10, 0.1, 0.2, so it's 39 point something. So then we need to look and see where it goes. So it's at least 39 point what? 3. It's at least 39.3, and that's where this thing comes into play. There's no more lines to determine exactly how much is present. So that's when you estimate one value. But the problem is, does it have to be, and I notice they say right here, 39.31, does yours have to be exactly that? No, that gives you some of your experimental error, and I don't mean that an error in a bad thing. I mean error in terms of it makes sure your results deviate a slight bit. Okay. Now, obviously, if you put 39.32, you're only off by 1/100th, and that's fine. But it gives you the ability to make a visual call, and that's where some of your data can change it up just a little bit. Okay. Now, so set up for titrating with an acid and a base. Again, what you're passing around is called a burette. Real quick, making sure we're on the same page. What is this thing right here? It is an Erlenmeyer flask. Okay. So here's the deal. We didn't do this slide, right? Okay. Do me a favor, and again, I know I'm writing this in a weird way. In the flask is going to be your unknown. Okay? The whole purpose of titrations is to determine the of a solution. I know I kind of wrote that very tight at the top. Determine what does a bracket and an X mean? The concentration of the molarity. So to determine the concentration of a solution. That's the whole purpose of doing titrations. Kinda. Yep. Okay. Now, in this burette, and I'm going to write it sideways, is the known concentration. So you're dripping a known into an unknown. Okay? And I'm going to explain to you how you then determine what it is. So let's pretend that we are dropping a base into an acid. You're dropping a base into an acid. You with me? Okay. So we're going to go drippy, drippy, drippy. And we're going to pretend that the concentration of the base is, I'm making it up, let's pretend that it is 0.25. We're just going to pretend. Okay? And I drop, let's say, 30.50 milliliters of that base into my acid. Again, what's the whole purpose of this thing? I'm trying to find the concentration of what? In this specific case, of the unknown, which in this case is the acid. Let's pretend that I started with exactly 50 mils of this acid. This is where I need some analytical kind of thinking. I know you know, you may not know that you know, but you do know what the answer to this is. Okay? My question to you is, based on the data that I have given you, is it possible to determine the concentration of the acid? Very good! Now, we don't necessarily want to use the ones. We can use something called MAVA equals MBVB. So, you've already seen this. You covered this in the video from Friday. Okay? Doesn't matter. Same thing. As long as it's on the same side. So, the whole point of perspective is we're trying to find the concentration of the unknown, right? So, what variable would we be solving for? We're trying to, because we need the concentration of the acid, right? So, very simple. MBVB over VA. Now again, I just made up every single one of those numbers on the previous slide, okay? I said that the concentration of the base was what, 0.25? Okay? I said now, this is the part that I think is important. So, this is the amount dripped in. The amount that is dripped in. Now, when I say dripped, I mean from the burette. Like you turn the little thing and it falls into it. Because eventually it will get to a point where you have to drip it. Okay? And what did I say? Was it 30? 30.50 mils. Okay? And we said the concentration of the acid was what? Yeah, excuse me, was 50. Yep, 50.0 mils. Hang on one second. So, my point is, I gave you three things. I need to know one of them. Is it a basic, simple plug and chug? That's all you have to do. If you know the concentration of one, and you need the concentration of the other, what two things do you then need to be able to figure out the missing concentration? You've got to know both volumes. Okay? One of them, you get to decide. Which volume did you get to decide? And I know this is kind of a bad way to ask this question. I don't think you're going to give me... It's the one that you started, the amount of acid that you started with. What does the experiment get to decide? How much you drip in. Does that kind of make sense in a weird, strange way? You get to pour in the amount of acid that you want to start with. That, you get to decide that. Okay? But the experiment will dictate which value. The amount that you're dripping. That's going to be specific to the drip. Okay? Because, very good question. Remember we said something about moles of acid equals moles of base. That's what we're looking for. I don't know. We're trying to find something called the equivalence point. Okay. Now I know what you're thinking, and this is gonna be like, oh well, duh. I understand what you're saying. My point is, when I'm going drippy, 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 how in the world am I supposed to know when I have reached the equivalence point? I can't use a microscope and figure that out. Very good. Now, not a paper, but a solution. And what is an indicator solution going to do visibly? Change colors. Okay. So when it changes colors, guess what you've reached? The equivalence point. So visibly, because remember there are 5 signs to a chemical reaction. All right, so and I want to show you video because I can't demo this because it is laborious. It takes forever. So I'm going to find a little video, but what you're going to notice is as soon as the drop of the acid, drop of the base mine, shut up. Drop of the base mine. Alright, slap of the base, man. That's right. Slap of the base. So what we're going to do is all of this stuff right here, this is going to be my known. Okay? And this blue is going to be my unknown. And we've already said that this is, what, 50 mils? Okay? And we said the concentration here was 0.25. So what we're going to do is every time this thing drips and hits this solution, in this acid, there will be an indicator. And what do indicators do? Change. There you go, change color. So visibly, I have to have the indicator or I could not physically tell. Now, will the same thing still happen? Yeah, but again, what's the purpose of the indicator? So your eyeballs, so you can see. Okay. So as soon as we get a definitive color change, you've reached your equivalence point. But here's the part that's important. When we do this, when you drip, it will change colors. But as we stir, guess what that color will do? It'll go away. And eventually, you can do one drop and it changes colors and never goes back clear. Okay. So let me show you a video. Let me find one real quick that can kind of help you visualize it. Told you it was 20 mils of acid, right? What was the concentration? Unknown. Now, I'm going to back it up just a grunt and watch. Can you tell it looks like the water's moving? All right, the reason it's moving is because there is something in there making it spin, that magnetic spin bar. So instead of you having to physically pick it up and swirl it like we used to have to do in the olden days, before all this new cool technology, we had to physically swirl the glassware. Now you put the magnetic bar in there, you turn it on, it just spins for you. So all you have to do is worry about the knob back and forth. Why do you have a question? Go ahead. Oh my gosh, yes. It's because it's spinning so fast you can't see it. Alright, so again, he dropped 2 drops of indicator. Again, what's the only purpose of the indicator? Your eyeballs can see the change in color. Now, there are 3 major indicators we're going to talk about. One, we're going to talk about brothomol blue, talking about phenolphthalein, and then universal. And phenolphthalein is really the big one we're going to use. All right, so that's phenolphthalein. It's clear in an acidic solution. What did he drop the phenolphthalein in? Into an acid. What color is it? Clear. When you drop a base in it, what color does it change? Pink. So every time you go drop and it hits, what should happen to the solution? A momentary pink thing. And what happens as that bar keeps spinning? It'll go away, because you remember, we're looking for something called the equivalence point. So we're trying to find when the number of moles of acid equals the number of moles of base. If I've got a big pot of water and I'm trying to make it salty, will one little splash of salt make it salty? Does that kind of make sense? One little splash of base, will it make it equivalent? But the more base I add, what's going to happen? The more your acid's going down and the more your base is doing what? Going up. That's an important concept. Why does your base not stay here? Why does your acid not stay here and your base rise to it? Why is it doing this? Say it again. Neutralization. I heard it come out here. So the acid concentration is kind of dropping and your base is coming up, so they become equivalent because of the neutralization fact. Okay? So, again, what's this little tool called? The burette. Now notice you can barely see it, but you can kind of tell here. It's 0, 1, 2, and 3. Why is the 0 at the top again? It's coming out the bottom, so as it's going down, it's easier to tell how much is coming out of it. All right, let me back it up just a grunt. So you can barely tell, but can you kind of see the meniscus? It's really hard to tell, but it's barely there. And again, this is the meniscus is sitting on that 0. All right, so notice he dropped it and it turned pink, right? Why did it turn pink? What's turning pink? The indicator. Now, it did it a little faster than I wanted it to, because what I wanted you guys to notice is that I wish it had showed this part of it, because as soon as it drops, it should have spun completely back clear. But I guess they kind of smoothed through, or went through the video. And now this would be your equivalence point. Do you notice how it's faintly pink and it never goes back clear? So here's the crazy part. If he adds one more drop, every drop makes it darker and darker and darker. You want to find the point when it is most faint pink as you can possibly find it. That tells you when you're at your equivalence point, because the darker it gets, the more you're going beyond your equivalence point. And that's why titrations are very specific, very particular, and honestly, they're aggravating because of how particular you have to be with it. You have to start over if you overshoot it. And really, in theory, back in college when we did this, we had to do the same titration 3 times, and we took all of our data and we averaged it out. Now, that takes at least 2 hours to do it. To get everything set up, to get everything done, and get everything calculated, it takes a long time to do it. The first time you do it, you go really slow, because you don't know where that, like if as you're opening it, it's dropping, right? Because you don't want to overshoot it. The second and third time, you're a little better because you know about when it's going to change. So the more you do it, the quicker it gets, because you know when to slow it down. Yes, I would. You basically, and again, it's all about understanding and feeling it. I've done this so many times, I know how to read it. But you guys, it's going to take you a little while to figure out the feel of how much do I let in. Because the first time you do it, I'm guaranteeing you to overshoot it because you're going to want to go too fast. Because it's like, I'm tired of watching this thing go drop by drop. It's just a part of it. All right, so we knew the original concentration. Now we know the volume of the base that was dripped in, right? Did you know the volume of the acid that we started with? So now can you calculate the concentration of that missing acid? That was MAVA equals MBVB, okay? So I want to go back and just kind of show you that one more time. I've never done it with a pH meter like this. So right here, I want you to kind of follow this. At the very tip of the mouse, that's the tip of the burette, and you can see little bitty drops falling out of it. And kind of watch the drops, and then watch how quickly the pH shoots up. There's your drips, and watch your pH. Boom. Each drop makes it change. Again, one more time. Each drop is a drastic change. It's quick. All right, so what this is now showing you, which we're going to get into in a second, is called your titration graphs. Okay, notice the most important part about a titration graph are the axes. Okay, look at your vertical axis. What is that? The pH. Now, we started, what's the x-axis? Volume of base added. So that's the drippy thing, right, in the burette. What was the pH before we ever dropped the drop in there? Yeah, thank you. It's 3 point something, right? So think about that. Is that an acid? Yes. Okay. Would it be considered possibly a strong acid? Possibly. Kind of just depends. I will tell you that based on this graph curve, I would say yes, it was an acid. Okay, and there's a reason why, and we'll talk about why later. Strong. Yeah, what'd I say? Excuse me. Strong. Okay, it's a strong acid. So notice what happens as you get to 10. As you get to 10 mils of base, what happens to the pH? At 10 mils, nothing. It's still flat. What happens when you get to 30? It might be a smidge above where it originally started. But then notice what happens when you get between 40 and 50. What all of a sudden happens? It takes straight off. Okay? Because what's happening is every drop of every drop of base that you're putting in the acid, it's getting closer and closer and closer till its equivalence point. Okay? Yes, it's running out of acid, and so the pH drastically changes. Because remember, when we're talking about pH, we're trying to count the number of hydrogen ions that are there. That's exactly what it is. In fact, the pH formula is pH equals the negative log of the hydrogen ion concentration. You don't have to worry about it. You just have to press a button. That's all you have to do. Okay? And the way you know when to slow down is when you take a drop, just one drop, and it turns pink and it holds that pink color for several seconds, and then it spins clear. We're not going to do the pH one. That's too complicated. Okay. So again, notice where the equivalence point is. At what volume? At about 50. I think it said it was 49, 40-something point, whatever it was. 46.02. So right there, you can barely see it, but 46.02. Because it's where the line becomes the most vertical. Okay? Tristan. Yes. Now, after the 50, notice what happens to the pH. It starts to go higher and higher, and then something weird happens. The question I always ask is, why does it not continue to shoot through the roof? Say that one more time. Very good. Do you agree that the base that you're dripping in there already has a maximum pH? Well, you can't make the pH all of a sudden miraculously go more than it was originally. So that's why it levels back off. So what you said is exactly right. The pH at where it levels back off is what the original pH of the drippy drip solution was. Yep. Yep. So would you agree if that burette was 50 milliliters, right? Okay. How much of that burette would you have to run all the way until you finally started getting close to your endpoint? Almost the entire thing, right? And there have been situations in the past in college where I was at like 80 mils of base, which what did I mean I had to do to that burette? I had to fill it up twice. Okay. And there are some that the acid is so strong, it takes a ton of base to reach that equivalence point. Think about it from this perspective. If you got in the ring with Mike Tyson, how many times would it take you to hit him to hurt him? A lot. If you put a really weak base in with a really strong acid, How much base does it take to affect that strong acid? A lot. Same concept. Does that make sense? Same thing for the reverse. If you've got a really strong base and a really weak acid, it takes a lot of weak acid to start to affect it. Now, the one thing I want to ask you about this, and we're going to look at from both perspectives. So, we started with an acid and we dropped the base in. Do you agree? How would this graph change if we started with a base and dropped an acid into it? It would be the mirror image of it. Would you agree? So we would start, the original at 0 would be way up here. Hang on. I don't care about all that. So what's going to happen is it's going to start like this. Matter of fact, let me see if I can... No, I can say that I have never actually had that happen. It would. So really what would happen is it would start like this, it would come out, and then it would eventually bend like this, and it's going to turn like that. So your equivalence point would be somewhere again, right in, that would be starting with a base and dropping in an acid. And again, I'm just making this up. Okay? But there are titrations that do that. All right? So let's finish, see what it has to say. That was it. That's awkward. Alright, so, now this is kind of weird. It says 25 cubic centimeters of HCl unknown compound. So what all was just given in that? What is cubic centimeters? 25, what I would have said, milliliters of HCl in an unknown, that either says compound or concentration. It says Just watch. Don't worry, cubic centimeters and milliliters are the exact same thing. Just accept it for what it's worth. What is most acid? Water. Yeah, okay. It's aqueous, water. Okay, so again, this is a burette. This is 25 mils of an unknown concentration. This is, I don't know exactly what that is, but he's fixing to drip this in there. Oh, he's filling it up with that. Okay. All right, notice what he just put in there. Kind of skip. Can y'all read that? It says phenolphthalein. Real quick, what color is phenolphthalein in an acid? Clear, and it turns what in a base? Pink. Alright, so we're going to titrate in. It's not called add, it's not called drip. It's technically called, we're going to titrate. That's the verb action. We're going to titrate in 0.1 molar sodium hydroxide. So do you agree we know the concentration? At the end point, or the equivalence point, will we know the volume of the base? We already know the volume of the acid, so then could you find the concentration of the unknown? Yes, alright, so let's see what happens. So now he's added some, and watch what happens when he turns it back off and swirls it. What would you expect to happen? Clear up until we get closer and closer to that equivalence point. Now, this is old school. This is swirling it, okay? Watch how it just clears up. See how each drop adds pink? Each drop. You see how tedious it is? It can get aggravating. That's why if you have that stir thing in there, it makes it so much easier. No, it was hand stir, just like he's doing. You could. It doesn't matter, really. Honestly, the size of the volumetric flask doesn't mean anything. In fact, you kind of want it bigger for what Dustin said, just in case you have to put so much in it you don't want it to overflow. You see, it's slowly taking a little longer for it dissolves. Can you tell? And see, do you see what I mean by if you add too much, you can overshoot it real quick? It's starting to hold it a little longer. And that's when, once it does that, you want to go more drop by drop than you do anything else. All right, it's getting close to the end point. Watch. Boom. Okay, now, if he stirs a little more, it'll thin up, but you want it a little lighter than that. That's kind of dark. So see how much you could read right there? It's between 25 and 26. So you're looking at about 25.3-ish, because you can't really tell because it's really fuzzy. There you go. I'd say, again, the angle may not be just right, but you could say 25.4-ish. That's where you get to decide. You could say 3.9, you could say 4.0, 4.1, whatever you would want to say. So they said 25.4 NaOH was used to neutralize. Notice how interesting. To do exactly 25 mils of hydrochloric acid. So we had a strong, and what was your volume? They were the same. So what does that tell you about the concentration of the acid and the base? It was a 1-to-1. So strong, right? So if you took the pH of the solution in the bottom of the Erlenmeyer flask, you had a strong versus strong, so what did it turn into? 7. About 7. That at the equivalence point, at that point. Yeah, you could have took it out and poured it, or you could have drank it. Now, obviously, I wouldn't recommend that with the indicator in it, but in terms of it being safe, it was absolutely safe. It tastes like water. Yes, or the original 25 was not exactly 25, or you misread it a grunt. So visually, did that help? Yeah, good point is the fact that, remember I said it was a little too dark? That if you would have removed 0.2 of that, that would have gotten a little bit closer. A drop matters. And again, it's kind of fun, but after you do it a while, you're like, God, this is boring. Like, you're just dropping a solution and watching the volume fall, and it can get, if you have to spin it like we used to have to do, it was awful. But now they've got those magnetic stir things, and it's easy. There is, the universal indicator is a rainbow. Yep. All right. It's very rarely used. Okay, so right here again, if you notice, a solution of NaOH is slowly added to a sample being analyzed. The sample is mixed, and the amount of NaOH added from the burette exactly equals the amount of H plus supplied by the acid being analyzed. The dye indicator changes colors. So that's kind of what's going on there. So these three things, actually, let's put a big circle around this. You may see this again. This is preparation for a titration. And it's what you have to do to make sure that everything is going to go over smooth, because if you don't follow some of these things specifically, it may mess up your titration. Number one is that a solution add a solution to the burette. Okay. The reagent reacts with the compound in the flask. An indicator shows when the exact stoichiometric reaction has occurred, which is called the endpoint. And when the concentration of the base equals the concentration of the acid, this is called the equivalence point, or it's called the neutralization point, if you want to look at it from that perspective. So I think this may kind of help you out visually. Now, this is why the titration reactions are so important, and how you're going to have to figure it out. So again, the axes on these graphs are very important. So what is your x-axis? Okay, it's the amount of sodium hydroxide you're dropping into the solution. What's your y-axis? pH, all right? So what was the original pH in that flask before you ever dropped anything in it? Okay, just under 3. Now, as you drip, first of all, what type of thing are we dropping into this? So we started with weak acid, and we're dropping a what into it? Strong base. This is, again, the concept of, if I put you in the ring with Mike Tyson, how much is it going to take to hit to hurt you? A lot, okay? But here's the deal. You are in the ring. I did probably say that backwards. So let's pretend that this is the boxing ring, and here is little old bitty you. Okay? And here, is Mike Tyson. Okay? You ever played the Nintendo game Mike Tyson's Boxing? There you go. Okay. So this is what's going on. You are already in the ring. Okay? And we're gonna consider you weak. And we're gonna consider Mike Tyson strong. If I'm dropping Mike Tyson into the ring with you and he starts punching on you, is it going to affect you very quickly? Yes. So look at this. Think about this. Okay? So, think about this. Look at the graph. Did a very small amount of the strong base affect that weak acid? Yes. Do me a favor. Circle this right here. This is what I call, and again, it's kind of weird, it's called a weak bump. And you'll see the difference in just a second. So the way you can determine if the original solution was weak is it has a bump in it. And what that means is as soon as that strong thing sucked it in the face, was it affected? Let me visually show you the difference real quick. Real quick. Hold your questions. Notice this one. Do you see a weak bump? No. So go back one more time. Boom, boom. So now we've got Mike Tyson versus Evander Holyfield. Yes, he bites ears, but that's okay. Can that strong base sustain longer without being affected as much? Yes. So again, we've got a weak acid, strong base. Now this is strong acid, strong base. So is there a difference? So there's two things we can talk about. Number one is knowing what we started with. We got a weak bump. The next most important thing is when and where does it reach its equivalence point. Now, the end point equivalence point are almost identical. What it means to be the end point is stop dripping. Because let me think about it. Remember when they just showed you those two things? They quit and measured the volume. If you kept dripping, would that mess up your calculations? Yes, you need to know when to end, when to stop. Also, if you kept dripping, would it waste solution? Yeah, there's no reason to waste the material. Because if you have to do another one, guess what you can do? Fill it up from that point back to the top. Logically, you with me there? Okay. So again, the end point just tells you to stop dripping. So this is also essentially what we call the equivalence point as well. Now, what I want to talk about is more the logic thing. What it says right here. It says that the equivalence point is above 7. Now, you guys know if it's above 7, what does that mean? It's a base. Now, look at that and tell me. All I did was drop an acid and a base, and when they were equal, it wasn't 7. You would expect an acid and a base to become 7. Why? Very good. Okay. So the reason why that the end point or equivalence point is above 7 is because what always wins? Strong. And in this example, who's winning? The strong base. So where does it push the equivalence point in reference to 7? Above or below? Above. So the reason it's above 7 is because we had a strong base. Hold that thought. Hold that thought. Okay? Now, if you did not see this graph, I did not show you this graph, but I did show you these words, and it was more of a, can you tell me an answer question? And my question would be, approximately, where would the equivalence point be in this titration? So the words, I'm reading the words. In a solution that is 0.1, can anyone tell me what that would be? CH3COOH. That's acetate, but what acid is that? It's acetic acid, which is vinegar. So they titrated vinegar with what? Sodium hydroxide. So my question is acetic acid strong or weak? Okay, so this is weak. What about sodium hydroxide? It is strong. So, again, this is an analytical question. Where would you propose or hypothesize the equivalence point being in that titration? Above 7, below 7, or at 7? Above, because why? Strong always wins. You with me? Does that make sense? Got a question? Okay, go ahead. Oh, nope, no, we're not going that far yet. Nope. Okay, I'm talking about this one only. Yes, that's why I don't like it. That's exactly why I don't like that version. Okay, what they're representing there is the fact that I'm not going to draw it. The hydrogen that is broken off is this one down here on the OH. Okay, all right. So now this is the next one. If I never even showed you any words or didn't tell you what any of it was, what are you starting with and how do you know? How can you tell simply based on the curve of the graph that you're... Okay, it doesn't have the bump, and notice how low the pH is. It starts at 1. Okay? Now, what are we fighting it with? The way you can tell it's a strong base is there's no bump at the top. And also, what do you notice the pH ending above? Above 12. That must be a what? Strong base. Now, we've got strong base, strong acid. Who wins? Neither. So where would you hypothesize your equivalence or endpoint to be? 7. Does it end at 7? Yes. Because guess what? Neither win. Okay? So that's why your endpoint, again, endpoint means what? Stop dripping. Quit. You're done. It's over. Okay? If you just saw these words in a multiple choice style question, no graph, no nothing, could you still determine where the equivalence point was going to be? How? Okay? HCl is what? Strong. NaOH is strong. So neither one wins, so that puts you at the equivalence point of 7. Yes or no? Yes. Now to answer your final question, actually, what is the only difference between... Watch with me for just a second. What's the difference between this graph and that graph? Now you start with a base, and what are you dripping? You're dripping acid. Visually, does that kind of make sense? I'm going to be honest with you. We rarely do this version. We normally do this. We normally start with the acid and drip in a base. Okay? All right. And to answer... Oh, it doesn't have the other alternative version. Thought it did. It does not. My apologies. This is another... Yeah, no, yes, it does. My bad. It does. No, it does. All right. So, what are you starting with, and how can you tell? Strong acid. There's two ways. There's no bump, and how low is the pH? The pH is at 1. Okay. How can you tell you're dealing with a weak base? Where does the pH end? At about 9. And notice where the end point is, which means what? Strong wins. So it pulls that equivalence point below 7. If I took the graph away and on a multiple choice test all you saw was these words, could you still tell me approximately where your endpoint or equivalence point would be? Where? How do you know? HCl is what? Strong. And H3 is what? Weak. Now do you understand how and why important it is to understand all your strongs? I've been begging you for weeks. This is finally getting you an understanding of, wait a minute, I got to do the net ionics and I got to know about titrations? Yes. And guess what? I told you this yesterday. This is a beach ball size Velcro ball. This is something that's not going to go away. All right, so standardize a solution of NaOH accurately determine its concentration. So here's my question. I want you guys to see if you can determine the concentration of the sodium hydroxide in that problem. So in this case, we're starting with a base and we're dripping in an acid. All right, so here's my first question. What are we solving for specifically in this problem? Okay, so we're solving for MB, which is MAVA over VB. So the molarity of the acid was 0.0998. The volume was 25.2 milliliters, all divided by 35.62 mils. Okay, Dustin, what did that come out to be? Did everyone agree or disagree? What was it? 0. What? And that's molar. We solve for the concentration. Milliliters cancel, leaving you with concentration. What is the concentration? Does that make sense? Concentration is molarity. Okay. All right. So now, so here's kind of what a graph would look like. Now, is this strong versus strong, yes or no? Yes. At what point was it neutralized? What volume was it neutralized? Okay, so we're going to pretend that this is 25. So at about right here, it's going to be your center dot, right? Okay, because it's at 7, and it's at about 25.2. That makes sense? Now, my first question is, it's strong, so there are going to be any bumps. Where is the 0 point going to begin? At the bottom or the top? At the... We're trying to do the base, so it's going to start at the top. Yes? Okay? And so it's going to be way up here by like above 12, correct? So it's going to come out like this. It's going to slowly dip down. It's going to hit here. And what was the concentration of the acid? It gave it to you. Sorry, so we're going to pretend that it's going to go way down here by 1. And that would be a basic, very basic sketch of what it would look like. Does that make sense? The key part is that your equiv point is at 7 and your volume is at 25.2 milliliters. What? Okay. All right. So, sources of error. What are some titration sources of error? You could use the NaOH was not exactly 0.1 molar. Like you're doing your calculations, your MB was not quite right. Your calculation errors, if you don't change it, which again you don't necessarily have to, not rinsing the burette with a titrant. Put a star beside that. Number 3, not rinsing the burette with a titrant. Now again, titrant is the stuff in the burette, and here's why. If you rinse that burette out with water, and then you pour all of the titrant in that burette and you begin, could that water have messed up the concentration of that solution? Which then goes back to point 1. It may not be exactly what you thought it was. So what you do is you pour it in there and you run some of it out, because what it's going to do is it's going to drain some, and then you fill it back up again at least maybe 2 or 3 times. Okay? Well, over-titrating, again, what does over-titrating mean? Too many drops. Okay? Ideally, 2 titrations should be done, 1 to get a rough estimate and 1 to get the exact value. Again, normally we will do that just to make sure that our numbers match. Acid or base left on the side of the flask or on the tip of the burette. For greater precision, water is used to rinse the tip of the burette off. And basically what that means is, what happens if one of the drops accidentally sticks to the side of the flask? Did it come out? It came out, but did it ever hit the bottom? No, and that could cause an issue as well, okay? Or if it's still hanging on the tip of the burette. It came out, and you could read it, but it may not have affected your solution, okay? Error reading volumes. Do you agree that reading that burette could be kind of tricky? If you don't read, because remember, it's opposite. So if you give it the wrong value. Using pipettes, basically, I don't really know why that would be wrong. And then using 10 mils of a base versus 20 to 25 mils, I don't know what that has anything to do with either. Okay? Yes, sir. Yes, it's always in milliliters. Okay. All right. Let's go back to this. Do I want to do this today, or do I want to? Let's start off fresh tomorrow.